On right where we left off speaking about cholinergic receptors and differentiating between ionotropic and metabotropic. And we saw an example for the ionotropic, which is nicotinic cholinergic receptors. These receptors also act as a channel, and so they are faster in their response, and they are much quicker in terms of generating a signal in the cell than the metabotropic receptors. The muscarinic receptors also bind acetylcholine, but they have a different effect in the cell. These are metabotropic. These are coupled to a G protein, and that is going to give us that whole second messenger cascade, which we're going to look very closely at towards the end of today. Okay, let's talk about some location of these cholinergic receptors. First of all, we have them on the autonomic postganglionic cell. And we looked at this example. So on the autonomic postganglionic cell, we have a nicotinic cholinergic receptor, right? So if we jump back to this image, right? On this postganglionic neuron, whether it's in the parasympathetic division, this is the parasympathetic division. If you look at the sympathetic division, all of your postganglionic neurons have nicotinic receptors. Okay, so we can see them here at this collateral ganglia. We can see them here on the adrenochromaffin cells. We can see them here on this postganglionic neuron as well. And then in the parasympathetic side, they are also found in the postganglionic neurons. So all postganglionic neurons have nicotinic cholinergic receptors. Let's get back here. They're also found in the effector organ for the parasympathetic system. So on the effector tissue, specifically for the parasympathetic side, why don't we see cholinergic receptors on the effector organs of the sympathetic nervous system? Why don't we see muscarinic cholinergic receptors on the effector organs of the sympathetic division? I want you to think about that for a little bit. So we only see muscarinic cholinergic receptors on the effector organs of the parasympathetic division. Why do we not see these receptors on the sympathetic side?
Because you're slow. You're slower and then you're faster when you're missing.
No, so they're slow. That's true, but that's not the reason we're looking for. So why do we not see a cholinergic receptor of any type, be it nicotinic or muscarinic, on the effector organs of the sympathetic division? Anyone over here? What kind of neurotransmitter do the sympathetic postganglionic neurons secrete? Norepinephrine and epinephrine. So would they bind to any type of cholinergic receptor? They would not, right? They would not. If we have a postganglionic neuron on the sympathetic side secreting norepinephrine, you do not expect to see any cholinergic receptor on the effector tissues in the sympathetic division. We will only see adrenergic receptors. Okay, does that make sense? Does that make sense? So in the sympathetic division, on the effector tissue, there are no cholinergic receptors. It doesn't make sense to have them. All right, we also see nicotinic cholinergic receptors on skeletal muscle. We're going to talk about that. We're going to look at the neuromuscular junction. And acetylcholine is the only neurotransmitter that plays a role in skeletal muscle. And so nicotinic cholinergic receptors are found there. And then I have at the bottom here sweat glands. We spoke about this as an exception. So the sympathetic division also has cholinergic receptors only for sweat glands. This is like a one exception to the rule. Nothing to really memorize. I'm not going to test you on this, but it's an FYI. Okay. So these are the locations where we see cholinergic receptors. Let's talk about adrenergic receptors. Let's talk about adrenergic receptors. First of all, what type of neurotransmitter does an adrenergic receptor bind? Norepinephrine or epinephrine. Now bear in mind this can either be a neurotransmitter as seen in the synapse or a hormone, right? So adrenergic receptors bind norepinephrine and epinephrine. There are two main classes, alpha receptors and beta receptors. And then within those alpha and beta divisions, there are several subclasses. So alpha 1, alpha 2, beta 1, beta 2, beta 3. Now, bear in mind, these are all coupled to G protein. So what type of receptor are these? Metabotropic, perfect. As long as that receptor is coupled to a G protein, this is a metabotropic pathway. It's going to be faster or slower? It's going to be slower, right? So just bear that in mind as we speak about these different types of adrenergic receptors. They are all coupled to a G protein, and so this is a metabotropic type of receptor. We're going to go through each of the categories one by one. We're going to speak about some properties, and I'm really going to point out the unique properties because they have quite a bit in common. So you really want to focus on the distinguishing characteristics or properties of each receptor in terms of testing purposes. So properties of adrenergic receptors is that they're located in the effector organs only on the sympathetic side. Okay. Alphas are the most common. They are also usually excitatory with the exception of alpha 1. We'll talk about that in a minute. And then they have affinity greater for norepinephrine than epinephrine. So alpha receptors bind norepinephrine more in a higher affinity than they do epinephrine. Okay, we'll see that's the opposite case for the beta receptors. So the important points here is that they're the most common, they're usually excitatory, and that they have a greater affinity for norepinephrine versus epinephrine. Let's talk about the beta receptors. So beta receptors all use cyclic AMP as their second messenger. And then they have different affinities for norepinephrine and epinephrine, which we'll look at individually. What do I mean by cyclic AMP as the second messenger? Let's jump back here. What do I mean by cyclic AMP as the second messenger? So we're talking about an adrenergic receptor. We said that it's metabotropic, meaning that it's coupled to a G protein. And what's the relevance of cyclic AMP in that pathway?
It can send down to the amplifier.
Okay, so the signal goes to an amplifier enzyme, and then we make a bunch of second messenger, right? And so, although this is a slower response, having this second messenger being produced is going to really amplify the signal in the cell, right? And for beta receptors, the only second messenger that we see is cyclic AMP. Let's distinguish some properties between beta 1, beta 2, and beta 3 receptors. So beta 1 receptors are usually found in cardiac muscle and in the kidneys. They are usually excitatory, and when I say excitatory here, I mean their effect at the tissue level. So excitatory can be speeding up the heart rate, can be increasing airflow if we're talking about the lungs. Excitatory simply means that you're activating that tissue, you're activating that cell. So they are usually excitatory in their effect on the cell or the tissue. They have equal affinity for both norepinephrine and epinephrine, which simply means that if you had a beta 1 receptor sitting on a cell, it would bind norepinephrine just as easily, just with the same affinity as it would bind norepinephrine. What did we say was the case for alpha 1? So we just talked about that. What did we say was the affinity? Which one? Which neurotransmitter had a higher affinity for alpha 1? Can you remember? For alphas, sorry, both alphas. Norepinephrine, good. So alpha receptors had a higher affinity for norepinephrine. Beta 1 receptors have an equal affinity for both. Beta 2 receptors usually in the blood vessels and smooth muscle, usually inhibitory, again, this is the effect at the tissue level or the cellular level, and usually has a greater affinity for epinephrine than norepinephrine. Okay, this is the one that sort of sticks out. So beta-2 receptors have a higher affinity for epinephrine versus norepinephrine. And then finally, your beta-3 receptors are usually in adipose tissue, also excitatory in their effect, and then again, equal affinities for norepinephrine and epinephrine. So beta-1 and beta-3, they really do not have a preference in terms of the neurotransmitter. They will bind both norepinephrine and epinephrine with equal